I'm glad to be here at BSides, and there will be more on the same topic as the previous presentation. So that was how VIP secure their APIs, and the focus was on a mobile client. This talk will be about where we use a web browser. And if you remembered from the previous presentation, the login with screenshot there. So imagine if you have a sort of open banking site or that where you want to log in with all the different bank IDs or support different bank IDs in the Nordic countries. Then there's a good chance that the clients you're writing are using OpenID Connect and OAuth to enable that and to drive that login flow. And if you follow the best current practices for this, then you will use a backend for frontend pattern. And I will talk more about that later on. And this talk is about security weaknesses and pitfalls, mistakes that are easy to make, even if you sort of have done your best and know the specs. And I'm Tobias, and I'm from Omegapoint Gothenburg, and we do penetration tests and security reviews. But me and my colleagues, we also work as developers, writing and maintaining code and helping teams with application security. So together we have a lot of strong background in both attacking and building systems with OAuth and OpenID Connect. And so we'll start with a little bit of history around OAuth and OpenID Connect and how we do secure implementations today. And it started out with OAuth2 there, and there was a lot of sort of custom implementation of OAuth login or OAuth, but that was a lot of weak implementation as well. Facebook and Microsoft and so on all have done mistakes implementing this, and to sort of address these things in the beginning, OpenID Connect was introduced and provided identity and login and sessions on top of OAuth. And but then OAuth and OpenID Connect was used in high security environments as well, and in bank and finance and healthcare and so on. So there was security profiles and best current practices. And the most well-known is the security profile for financial grade APIs, but that applies to any business with high security requirements. And then we have the best current practices for OAuth, and they gathered under OAuth 2.1. And this has a lot of specs, and probably like a 2-day workshop at least to go through all that. So for this talk, I will give you sort of a 2-minute version of how we do secure applications following those specs. And so the basic thing here is that if you have service-to-service where no user interaction, then you use something called OAuth client credentials. And you strengthen that with strong client authentication, not just the basic authentication for the client. Instead, you use mutual TLS or something called or JVT assertions. We saw those earlier, the signed, looks like access tokens almost. And then, if you do that, you can do sender constrained access tokens, which they also mentioned in the previous talk. And you you link the access token to the certificate that was used. And you can use mutual TLS or something new called DPOP. And of course, you should have short-lived access tokens and sort of follow least privilege. And especially for third-party clients within banking and finance, maybe concerning the PSD2 directive, you should definitely consider reference tokens to not leak information outside your organization and being able to revoke the tokens fast. So that was the service-to-service. And when we have users, then it's more complicated. And we use the code flow. And the OAuth code flow is when you just want to have consent to delegate authorization to a third-party application, for instance. But when we do login, it's OpenID Connect code. It's it's a similar flow, and we want to really distinguish between the two here. The things I will talk about concerns them both. And we can, since we use this BFF pattern, we have a confidential client, a backend client. This means that we can use the same hardening techniques as we did with the client credentials there. So we can apply things like strong client authentication and sender constrained access tokens, even if the user is using a web browser. And of course, we should follow the best current practices and FOPI and apply additional protections with the code flow. PXE is mandatory. PAR should be used, but it's kind of new. Very few support it today. But hopefully in the next year, that will be better supported. And yeah, so this was the 2-minute version. So if we follow all this, is the problem solved then? Are we secure? And unfortunately not. Because in reality, many implementations, they don't do this BFF pattern. So they handle access tokens in the browser, in JavaScript frontends, which is a very hard environment to secure. So it's very hard. You can't keep secrets there, and so you should avoid having tokens there at all, if you can. And most implementations, they don't bother with client certificates. I mean, it's quite boring to deal with and keep them rotated and things like that. So it means that a lot of things happen with just basic client authentication and kind of static client secrets, perhaps. And then we have its bearer tokens. They're not sender constrained. I mean, VIPs do it well, as we saw. But if you don't do this sender constrained tokens, then you can just steal a token and use it from whatever you want. And then we have this PAR that's not supported. So so there are a few things here that open up for different attack vectors. And to understand these attack vectors, we will start by looking at the implementation with the 2019 best current practices. That's ages ago. So whoever built apps like that and hasn't updated. So if we look at the current best practices, there really is a current there. So it's important to stay updated. And if we look at how that's a SPA here, a single-page application running in the browser, it looks like this. We have this token service or identity provider, and the token request and the authorization request, it all happens through the browser. So the token will typically be stored in local storage, is a common place to store the token. And then the SPA here can just attach the token. We saw the authorization header with the bearer and the access token there, usually a JSON web token. And they can call the different APIs here. And there could be a lot of APIs, of course, in this sort of microservices architecture. Here we just have two, but the product API and the order API. And what's interesting here, to get a little bit of context, is that, of course, the logged in user should be able to get the products this user can access, not other products. And the logged in user should also be able to get the user's orders, not orders for other customers. And the logged in user should definitely not be able to use this endpoint get all orders that is meant for system integrations to sort of access all the data in the system in a easy way. So the sort of ultimate attack here is that the attacker can execute the get all orders call there. And one thing that we should note here is that if you have been following the best current practices from 2019, you have built this way, and then you also probably use something called a silent renew, because access tokens are short-lived, and we can't bother users with logging in every now and then, like every 5th minute or so. So then there's something called silent renew, and that means that the SPA there will silently in the background call the token service for new tokens, and it will get new tokens because it can present a session cookie to the token service, which also sometimes referred to a single sign-on cookie, because that also enables single sign-on. So the attack there, to get all orders. How can we get a token to get all orders? And this is a way to steal tokens. Cross-site scripting is common. It's less common these days, but in an old application like this from 2019 or something, it's a good chance that we have a cross-site scripting vulnerability. And if we can inject code running in that application, there are other ways to inject code like supply chain attacks and things like that. But we discussed cross-site scripting here. Then that code can do the same things that your application code can do. And that means it can silently renew tokens and send those tokens to the attacker server. And from the attacker server, we can access the APIs, just like the application would. And so that is, of course, not a good thing. And one thing to note there is that there might be clever attempts to hide tokens in the front end, but you really can't do that. And if you want to look closely on this with the nice demos, then Philippe Deric had a great presentation on NDC security earlier this year that I can highly recommend, available on YouTube. So how can we fix this or make it harder at least? Of course, we refactor to the best current practice of today. And this means introducing the backend for front-end pattern. And then it looks like this. And we have introduced this backend, which is a dedicated API for the front-end application. And it holds the session, and it will also hold the access tokens. And the SPA is basically exactly the same. It's now served from the backend for front-end. And all the JavaScript code, quite complex code, has been removed. Instead, we have moved that code backend. So everything, the token request now goes from the backend to the token service. This means that this backend is, the client now is a confidential client, not a public client running in the browser. So we can use things like mutual TLS and send the constrained access tokens and things like that. And another thing to note there is that we now secure that session with a session cookie that is properly configured. You could, of course, do mistakes here and have an insecure session, but that's not the issue in this talk. So it's secure. And then we have also introduced to really raise the bar here, we have applied infrastructure protection as well, so, which we missed earlier. So because now we have this backend for front end, the other APIs, the backend APIs, they don't need to be public on the internet anymore. So we can introduce a gateway or firewall and make them internal, which is great, because you shouldn't really expose internal APIs on the internet. And of course, this picture, we don't have the infrastructure protection in front on the BFF there. It could be a web application firewall and so on, but attackers are quite good to bypass those. So that's not in the picture. And so this is what we have, and it seems pretty bulletproof, right? It's very hard now to get all orders, and there are no tokens in the front ends to steal anymore. But the cross-site scripting vulnerability, it still exists. It's really hard to keep a front end secure from cross-site scripting over time. So, and with if the attacker can inject code in your application, then they can now do session writing, of course. So they can do anything the user can do with the user session there. So it's a more limited attack than previous, but it may still be quite bad. So what can we do if we can do session writing in this context? Well, it's hard to tell without proper testing, perhaps pen testing or your own security testing. And we can start by looking at the requirements for this access model that we have here. And the first here is that we should be able to get product 1 because the user has access to product 1. That is a success. We should be able to get the orders, our own orders, not other customers' orders. Quite easy. And then we have this orders all. And it's a little bit more, we need to think about that a little bit more. So should return all orders, but only if the caller is authorized for this all access. And to make this maybe a little bit easier to test, we can rewrite this as 2 test cases. Should return orders if the caller is a system integration. Should not return any orders if the caller is a logged in user. And that's typical, that's the attack. So it's really a good thing to have those negative test cases for possible attacks, because that is what the attacker tries to do. So, and if we run those on our implementation we saw earlier, we have all the defenses, we have followed the best current practices, but unfortunately the last one fails here. We're actually able, by just changing the route and still accessing the orders all endpoint, even if it's not exposed on the internet. And that's surprisingly, if you ever end up here, and and not good. So how did that happen? What enables this attack? And if we look closely into this picture, we will start looking at the BFF here. What does it do? It's routes, and we see the stars there. So a default configuration for many reverse proxies or gateways like this is to look something like this. They have a whitelist for hosts which they can route to, but often it's sort of default catch-all routing there with the stars, which means that they will route to anything that you pass in there, not just the ones that the backend for frontend should be reaching. And since the backend frontend can reach the host, it should make calls to any endpoint there. And yeah, so that's not good. We have the stars there. And besides proxying requests, what else does the backend frontend do? Because I mean, those were public before, so it can't be that bad. But it also attaches the access token connected to the user's session. So that means that you can hit any API inside here with a valid access token. It may not be valid for that endpoint you're hitting, but does your average API do proper access control? Well, the stats are against you, perhaps. But because if you look at the top 5 here, it's almost all broken auth in some way. So it's a pretty good chance that the API here, it sees this token and it will accept the call. And but there are actually 4 issues here for this attack to succeed. And if we look at that, we need to access a low privilege session. In a larger organization, it's quite likely that during some point the attacker will be able to get hold of an account or misuse the session. In some system, you can also sign up to get a low privilege user, so that's really not an obstacle. And then the BFF here, it needs to have access to the API hosts on the internal network. And especially in the cloud, perhaps, but also on-prem, it's quite rare to see network segmentation between the backend for frontend and the APIs. Maybe you have network segmentation to the databases and so on, but between those web hosts, it's rare to see network segmentation. So that's quite likely that you can access, and especially since this microservice architecture here, it sort of maybe drives that the BFF should be able to reach every host to get some endpoint, and you mix host system integration points. Endpoints are hosted together with the endpoints for users because it's easier to maintain and deploy and develop and so on. So you can't really count on network segmentation to solve this. And then we have this catch-all routing, and that's just a common default. So it's a pretty good chance that that's in place as well. And finally, we have the authorization bugs in the APIs, which also is likely. So it might seem that a lot of things should be in place for this attack to succeed, but in reality, it's not that unlikely, and it's definitely a risk that you should consider. And so how could we mitigate all this? Well, as always, the guiding principles here, zero trust, least privilege, and defense in depth will sort of guide us in the right way. And talking about how we should apply this for a system like that is a talk of its own. So we'll focus on 2 things here. proper access control in the API, and the routing here with the BFF, that it only should route valid requests. And if we start with the BFF routing, that's kind of easy to fix, but it's boring and maybe hard to maintain. But there really is no way around having a strict allow list to close this possibility for an attacker to hit endpoints you're not supposed to. And don't try to be clever here and introduce sort of patterns and regular expressions and things like that. Pen testers and attackers are really good at bypassing those kind of clever things. So just do a strict whitelist or allow list. And so it solves the problem. But from the previous slide, we should apply defense in depth and security in multiple layers. We shouldn't just rely on the routing here. It could be easily misconfigured, right? So of course, we should also handle the API authorization. So if we apply this whitelist, the routing is resolved, so no stars there anymore. So this API authorization, why is it so hard for APIs to do proper access control? And this BFF pattern here, sometimes it makes it a little bit harder, and it concerns the scopes, and they sort of add some challenges to the APIs here. And so now we'll look at that. And so if we look at the authorization request that initiates the login flow here with the OpenID Connect and the code flow, it looks like this, and it goes through the browser. And we have done a lot of security, and it's quite easy to forget that no matter what we do, the attacker would always control this and can change this. But state redirectory, client ID, they are all validated, and it will be a bad request if the attacker changes anything here. But the scope here, that's by design. The attacker can add, or the user can add any scope that the client has access to. And why is that so bad? It's sort of by design, but so if we just add scopes there, so because scopes are easy to misconfigure, it's hard to keep this least privilege when you do client configuration. You might be reusing a client for different applications, for different scenarios. For instance, you might combine a client where user do login, but also with system integration. If you do that, that means that a user that is logging in can add the scopes only the system integration should have access to. And then they will get an access token with those scopes when all this redirects and the login is done. And also APIs could misconfigure how they interpret the scope, for instance. So keeping the least privilege there is really important. And so we should of course only configure the scopes and flows that the client actually needs, and try not to mix those roles. And if you have high privileged endpoint, then it could be quite risky to just base authorization on the fact that the token is valid and that it has the correct scope. You could use something more like perhaps the client ID or authentication method and so on. And then of course this sounds really weird. Why should the user and attacker control what scopes are in the authorization request? If you have a consent page, that makes perfect sense, because then you select the scopes and that's part of the design. But if you're logging in, there is no consent, so why? And for that we use PAR, and PAR is like this, and then the authorization request only has those two parameters, and if any of those are changed, then the request will fail. So the scopes are sort of pushed from the back end, and this is a reference to those scopes. So now we closes that attack vector, that someone actually changes the scopes there. So that's a good thing, but not supported by token services yet. But RFC is there. So this was one part of the scope issue. Another part here is that you might end up with really, really powerful access tokens. And if the access token is very powerful, then it's harder for the API to make the right decision. So if we look at what we have here from a little bit of different perspective, the backend for frontend here will have an access token. In order to provide the user with all the functionality it needs during its session, it must get an access token that has access to all this functionality, which means all the scopes and audiences. And depending on your system, it could be all the scopes you have in your system, because it needs to get user data from all those microservices. And so that could be a problem, and it could also looks like this, sort of the chained pattern here, which is a challenge for OAuth implementations. And as you can imagine, there can be a lot of scopes and a lot of access if you just sort of pass along the original token. And that token could then become sort of a glorified API key with access to all the APIs in your system. And that might be fine, or a risk you're willing to take, but it could be really catastrophic if, for instance, the API 3 here may be another organization or a much weaker protection, because API 3 will have an access token and can start misusing that, hitting API 2 and 1. So that's one way to leak tokens. So scopes design is quite hard in larger organizations and worth spending time on. And one way to deal with this, to sort of have more of least privilege for tokens, is to create a new token. You have the token for API 1, but API that is not valid for 2 and 3. So API 1 needs to do client credentials and get a new token. And we have like this. And then we solve this scoping issue, because then you only need the scope needed for API 1, and you have least privilege there. And that's good. One thing that you might run into is that tokens get too large for the HTTP header, and that's not a good design, because then you probably have too powerful tokens and need to sort of redesign. A good solution to that is not to increase the max size of the HTTP header for the web service. So this solves that problem, but it introduces another, and now it's kind of hard to have the traceability or accountability that the user actually initiated this call, because API 2 there only sees API 1. So to handle both, we can use something called token exchange. That's also not supported by many token services, but there are definitely a lot of them that do that. Then we pass the original token when we change the token, and we will get this ACT claim in the token that provides us with this chain of traceability, so we can know how the request has been. So this handles both. And if you don't use this, then understand the risks you introduce. Maybe accountability is solved in another way, so it's not needed, or you're comfortable with having sort of global access tokens. And we should note here that this least privilege for tokens, it doesn't solve the session riding in any way, because the attacker who does session riding in the backend for frontend there will of course be able to do anything the user can do. This will only limit the risk of leaking a global access token, but the session riding remains there. So with this, I have shown how to build a secure OpenID Connect OAuth implementation and following the best current practices. And it will look something like this. And then we talked about how to avoiding some common pitfalls concerning the routing and the scopes, and how that may affect how APIs can deal with authorizations. And it's time to summarize. And the first thing here is that please read and follow best current practices for OAuth2 and OpenID Connect. The FAPI here is very detailed on guidance and how to implement things. So I can really recommend that. And there's a version 2.0 right now, and that's more easier to digest than the first version. But so that's important. So even if security should always be proportional to your business. So even if you're not sort of in the healthcare or more finance and have those high requirements, then it's important to understand what protections you have and the attack vectors that exists concerning those protocols. So you know what you're. So if you choose to, I will stick with bearer tokens, and that's maybe a perfectly good choice for your business, but you must understand the risks you introduce. So it's quite good to understand those, regardless of what level of security you're at. And then of course, for basically any application, stop handling access tokens in JavaScript frontends and start using the backend frontend pattern with a strict allow list. So we don't. So this, it's a little bit unfortunate. We have invested a lot in security here, and we shouldn't end up with a vector for authenticated server-side request forgery by having this wildcards routing. And then, of course, proper access control in the APIs. And we will sort of help to make this easier by following least privilege, both for client configuration and when we do token requests. So even if the client has access to a lot of scopes, it shouldn't always request tokens with all those scopes. And finally, when we have a browser-based application, cross-site scripting is a really, really serious problem if we're vulnerable to that, because session writing is usually really bad, and if someone can run code in your application, then they, of course, can always do session writing. So, yeah, that was it for me. Any questions?
Questions?
Hi, thanks for the presentation. My question is, if we store access tokens, for example, in secure HTTP-only cookie, would that mitigate majority of the risks that you mentioned about handling access tokens in JavaScript frontends?
Yeah. In a way, it's stronger to keep them in the backend, but storing them in an encrypted cookie not reachable from JavaScript means that a cross-site scripting can't really access that. But having a powerful token on the client means that if you have control over the client, then maybe you can get that token. So it's better to keep it in the backend, but if the encryption is strong, then it's really hard to get that token. So yeah, so because some frameworks, they do that by default, .NET for instance, and so if you have it in an encrypted cookie, then you get less state issues with the backend. But since if you want to add things like, if you want full control over a session, you want to be able to force the user to log out or end the session, then you need complete control on the back end anyway. But if you're sort of in a little bit of lower security requirements, then that could definitely be a solution that's good enough. And yeah. Yes?
So the best current practices for SPAs also has a recommendation if you can't do the BFF or token service pattern by using web brokers. What are your opinions on that?
Using web brokers in order to keep tokens more secure in the SPAs.
Correct.
Yeah. That's it's SPAs. It's very hard to secure the JavaScript front end, and if you can run code there, you can use this silent renew to get the tokens and so on. So the tokens are less protected in the in the front end than in the back end. And I think the recommendations for high security environments are quite clear that you shouldn't have tokens in the front end, even if you try to hide them in web workers and things like that. I really recommend Philippe Deric's presentation from NDC Security on that topic.
Any other questions? Looking up at the balcony. Anybody? Don't let your BFF be a vector. That's it? All right. Everybody's got it. Thank you very much. Oh, here we have a question.
What do you see for the future?
Well, concerning web applications, I think the protocol has sort of settled, and I think maybe there won't happen much. But concerning mobile applications and how you do a good user experience logging in on that, and also utilizing the possibilities to do biometric login and the fact that you have a really powerful device in your hand, sort of the touch flows and the VIPs there, and we have the WebAuth2. So I think there will be integrations with that will sort of change things, and there are some new parts concerning those flows that probably will happen during the next years. So I think the integration with WebAuth2 will become more common and clearer. Yeah.
Anybody else? I have a question. I'm wondering if there's anybody who's into bug bounty and wondering how they could look for this stuff. Do you have any tips for a quick and efficient discovery and validation of these types of issues?
Yeah, we often work with the Portswigger and the Burpsuit tool when we do penetration tests, and they have excellent labs and how to sort of attack and explore attack vectors around concerning this. So that's a good place to start. Otherwise, the specs there, and they have an excellent threat model around OAuth that I highly recommend reading, and that could give you some insights on how to attack those kind of systems.
Great.
And do ethical hacking, of course.
It's very important.
Yep.
All right. If there are no more questions, then let's give a big thank you to Tobias.
Thank you.